Okay, so here's our next video on continuing chapter 7. This is 7.3, learning target 22, which is using properties of logarithms to rewrite expressions. And so we have a few different properties we can use to rewrite logarithmic expressions. These are really important to be able to simplify different things, especially when we start doing calculus with exponential and log functions, where we have to take derivatives of them, or next year when you have to take integrals of them, that in one form they might be really difficult to solve, but in a different form they would be much easier. And so this is where it's really going to help you to be able to condense and expand logarithmic expressions. It also helps when you have to solve equations, both just in a general setting to solve an exponential or log equation, and then also, again, when you're taking derivatives and integrals of things, like when you do maximum and minimum problems with a derivative, you need to solve for critical numbers. You'll need to solve an equation that could have a log in it. So the first formula we have is a change of base formula. So this comes out of a long time ago when people didn't have calculators that calculated logs. They had to use these things called log tables that could that had like all the logs listed for certain bases, and then you had to be able to convert from whatever base you wanted to the base that was in the book or in the table. It still serves purposes today in terms of simplification. It doesn't have the calculator use as much anymore because a lot of calculators can calculate logs with different bases. But even now, not all calculators can do that. They have a log base 10 button and they have a natural log button, but they don't really usually have buttons for the other logs or ways to enter other bases in. And so the change of base formula says that if you have a log of any base, let's say base A of B, then you can write it as log base 10 of B divided by log base 10 of A, or natural log of B divided by natural log of A. In fact, you can make it any log base you want. This could be log base 7 of B divided by log base 7 of A. Now that isn't particularly useful, but it basically says that the proportion, the ratio of these bases with the same log base would be the same regardless of which base you used. So most commonly, we either convert it to log base 10 or to the natural log. Very often natural log, but log base 10 as well. A way you can think about this is it's like a scaling. They're all constant multiples where we're multiplying a base, a log by a 1 divided by something. So for example, if I asked you to find log base 4 of 25, that would be the same as log base 10 of 25 divided by log base 10 of 4, or natural log of 25 divided by natural log of 4. And then you could type that in your calculator much easier and get the decimal approximation for it. You also have a few properties of logs. This helps you condense and expand different expressions. And they correspond a lot to properties of exponents. So the first one says that if you have a log base anything of 2 inputs multiplied, then you can separate that using the same log base, but you can make it an addition of 2 terms. This is similar to, whoa, I don't want that zoomed in. This is similar to when you have in exponents, if I have a to the v, a to the u times a to the v, that's the same as a to the u plus v. Right, that's the analogous expression here. It's these two things are exponents that get added up. The next property we have is if these inputs are divided, then you can subtract them. Again, just like with exponents, if you divide two terms with the same base, you can subtract their exponents. And the last one is the power property. This says if you have an input raised to a power, you can bring that power down as a coefficient to multiply into the expression. And this is similar to if you have a power to a power, you can multiply those two powers. So these properties all come out of those exponent properties because logs and exponents are connected in this inverse relationship that they have. But these are your three main log properties to use, remember, and be able to simplify expressions with. So you have a bunch of problems in the textbook that deal with expanding and condensing logarithms. The last thing to do in this section is called curve fitting. So this is where a lot of times we'll have function data given to you, and it can look linear, it can look quadratic, it can look exponential, and you can write an equation for it. Well, sometimes we can make things logarithmic. In fact, you've seen this a lot in the news recently. When we think about exponential growth, a lot of times those graphs, because in an exponential growth model, it would look like that. That's really hard to see because the scaling is so different, right? So like this, at this point it might be 2, but over here it might be like 1024. And so the difference in that scale is really hard to show when you have limited space to show just how different and like how much of distance is in between 2 and 1024. And so a lot of times we want to make this look like a line. Line's also easier for people to understand. And so instead we change things to a logarithmic scale. And when you take exponential growth and you make it logarithmic, you make all of these natural logs or log base 10s or whatever, it ends up making a line. So exponential growth, if you just use x and y, looks like an exponential growth curve. But if you make it into a logarithmic scale where you count by logs rather than by, so you count by the exponent, right? So instead of counting 2, 4, 8, you would count 2 to the 1, so 1, 2, and 3, because 2 to the 1, 2 squared, and 2 cubed. And so you get this equation format, which is y equals mx plus b, but we're making the x and y values log values. We're making a logarithmic scale. And that's going to look linear if your data is exponential. So let's do an example of a problem like this. So we have some data given to us, and we want to find a logarithmic equation that relates x and y. So looking at just x and y by itself, if I want to find a slope here, well, this is plus 0.189. This is plus, let's see, what's 1.316 minus 1.189. That's plus 0.127 and 1.414 minus 1.316 is plus 0.098. Right, so there's no constant slope here. This isn't a linear equation. But let's see what happens when we take the natural logs of each of these values. So we'll take natural log of x and natural log of y. So the natural log of 1 is 0. Natural log of 2 is 0.693. Natural log of 3 is 1.099. For 4, it's 1.386. For 5, 1.609. And for 6, 1.792. Then we'll do the same thing for the y values. So natural log of 1 again is 0. Natural log of 1.189 is 0.173. Then 1.316, 0.275, 1.414 is 0.346, 1.495, 0.402, and 1.565 is 0.448. And so now we can look at this slope. So change in y over change in x, right? So we can do it on this point. Well, the change in y over change in x would be 0.173, and the change in x is 0.693. And so if I divide that, I can get my slope, right? This is slope. And I get 0.250. And I can check it at some other point just to see if I'm getting a similar slope. So let's do it over here. So 0.402 minus 0.346 divided by 1.609 minus 1.386. And here we get about 0.251. So with this curve fitting, because we have this data and we've rounded a few times, it might not be exact, but it's basically 0.25. So as long as you pick a slope that's similar enough through this table, that can be your general slope. Remember, we are curve fitting, and this data isn't necessarily completely exponential or perfectly following that curve. It's kind of like a regression thing. Like if you wanted to be really correct, you would do a regression on this. But this is still a way to approximate without doing a regression, but getting an equation that would mostly fit the data you have. So then I can write this equation. Natural log of y equals slope of 0.25, 0, natural log of x, plus b. And then the b value is the y-intercept. Well, I have the y-intercept over here. It's 0, 0. And so b is just 0. So this is natural log of y equals 0.250 natural log of x. So that's your basic logarithmic curve fitting process that you'd have to do. So you have a few more examples on here that you can try. So I would have you try these on your own and check. And really, it's just take the natural log of each and check them. If you want to send me your work, if you're not sure about something, you can ask me a question on it. But I think it's mostly self-explanatory and straightforward. And this problem is on page 494 in your textbook as well, so you can look at that to help out too. So that's 7.3. It's the properties of logs. Mostly just know how to expand and condense logs and do this curve fitting stuff.